Hey everyone, welcome to our video today about local linearization or linearity. So today we're going to take a look at approximating values based off of a tangent line to a curve. All right, but before we do that, let's talk about curvature as consecutive lines instead. If you look at this figure over here to the left, you might think it's a circle. But as we zoom in closer, it's really not. It's not a circle. It's actually a many-sided polygon. Okay? It's actually a 24-sided polygon. Okay? Its technical name is a icosahedra. Try to say that a couple times really fast. When the number of sides becomes this large, the length of the sides becomes really small. Okay? The calculus definition of a circle is simply a polygon whose numbers of sides approaches infinity and whose length of the sides approach 0. So we get more and more and more sides, but those sides get smaller and smaller and smaller. The above phenomenon occurs actually in real life, often. Think about guardrails on a curving road. Now, here in Illinois, we don't have a lot of roads that look like this, but if you're ever driving in a place that's mountainous or very hilly, you might see guardrails on the side of the road. Guardrails are not in themselves curvy. They're not matching the curve of the road, but really it's just a bunch of straight line rails pieced together so it looks like a curve, okay? So since the straight line sections of railing are very numerous, they appear to curve with the road when really they do not. Another thing you might have seen before is a wooden roller coaster. Okay, it's very difficult to create curved wooden rails. So they use straight planks of wood, and when there's many of them and they're connected together and they're not really that big, they can simulate the curvature of the coaster's hills. Okay, so what is linear approximation? Okay, so we have a function f and its tangent line at a point. So over here we have a function f, and then we have a tangent line at point A, f of A. The equation of a tangent line, we'll call that L of x. So this tangent line we're going to call L of x. It's given by this equation. You can see all this is here is basically point slope form of a line, y minus y1, and then the slope x minus x1. And then what we want to do is we want to add f of A over to the other side. So some people write it the point first, some people write it with the point last. It doesn't really matter. It's the same equation. So if you write it as the point last, it would just look like that. Okay. So obviously, if you look at this picture over here, really close to that point, the tangent line and the curve are really close together. So if we picked an x value really close to A and got an approximation on the tangent line, it would probably be pretty close to the actual value of f of A. Okay? But as we get further and further apart, so now we're over here, you can see there's a pretty big gap between the function and the linearization. Okay? So we want to really only use this for x values that are close to the point that we're drawing the tangent line in at. Okay? So we call this tangent line the linear approximation to the function at x equals A. Now, obviously, every function has infinitely many linear approximations depending on which point we choose. So we're really just looking at one point. We're going to call it x equals A. All right, let's take a look at what this might look like here. So it says use a linear approximation for f of x equals the cube root of x at x equals 8 to approximate the cube root of 8.1. All right, so we need, just like anytime we're writing a tangent line out, a point and a slope, right? So if we wanted to find our point, we would just put 8 into our equation, and that would be 2. All right, if we want to find our slope, we need to take our derivative. And that would be 1/3 x to the negative 2/3. Or if we wrote that without a negative exponent, 1/3 x to the 2/3. And then f prime of 8 would be 1 over 3. 8 to the 2/3, so that's 8 squared, and the cube root of that, so the cube root of 64, which is 4, and then that would be 1/12. So our linear approximation here would be L of x equals the y value, plus the slope times x minus the x value. So that's our tangent line. All it is the tangent line that we've been working with all year, really. The only difference is we added the 2 to the other side. Okay? Sorry, I missed the 12th there. Okay, so now we can use that approximation to approximate any value near 8. So the question is asking us for 8.1. So we simply put 8.1 in for x. And we get 2 plus 1/12 times 0.1, which is 2 plus 1/12 times 1/10, which is 1 over 120. So 2 and 1, 1/20th. Or if you want to write that as an improper fraction, 241 over 120. And of course, if you prefer a decimal, as long as this is a calculator question, you can put that in. So we're saying that the cube root of 8.1 is approximately this number here. Okay, is it exact? No, it is not, but it's probably pretty close to that number. Okay? So the cube root of 8.1 is approximately 241 over 120. All right, let's take a look at another example here. It says using a calculator, find the error and using the linear approximation to f of x equals e to the x at x equals 0 to approximate the 4th root of e. All right. So again, we're going to need to write a tangent line out in order to do this. So f of 0 equals e to the 0, or 1. So our point is going to be 0, 1. F prime of x is just e to the x. F prime of 0 is also e to the 0, so it's also 1. So our tangent line would be y minus 1 equals 1 times x minus 0, or y minus 1 equals x, or y equals 1 plus x, or x plus 1. So L of x here is 1 plus x, or x plus 1 again. All right, so if we want to find our approximation here, so so the 4th root of e, remember the 4th root of e is the same thing as writing e to the 1/4. So x here is 1/4. So L of 1/4 equals 1 plus 1/4, or 5/4, or 1.25, depending if you like fractions or decimals. All right, now if we want to find the actual answer for this, we can use our calculators to help us with that. So that first number is our approximate answer. Our actual answer, so f of 1/4. If you put this in your calculator, you can do e to the 1/4 power in your calculator, or the 4th root of e in your calculator. You're going to get approximately 1.28403. Okay? So to find the percent error for that, not percent error, sorry, just to find the actual error for that, to do the error, you do the absolute value of the actual value minus the estimate value. All right? So in this case, it's going to be 1.28403 minus 1.25. The absolute value of that is 0.034. So our tangent line approximation is 0.034 away from the actual answer to this problem. Pretty good. Again, because the x value was close to the linearization point that we chose. All right, third example here for the tangent line to f of x at x equals 4 to have an error of at most 0.1 when approximating f of 4 plus h, find the range of values for h. All right, so the first thing we need to do, again, is to write our tangent line out. So f of 4, if you put 4 in here, you get 16 minus 12 plus 5, that would be 9. So our point is 4 comma 9. F prime of x would be 2x minus 3. So f prime of 4 would be 5. So our tangent line would be y minus 9 equals 5 times x minus 4. So our approximation would be 9 plus 5 times x minus 4. All right. So now we're going to find our actual value and our estimated value. So our actual value, f of 4 plus h, if you put 4 plus h in here, we get 4 plus h squared minus 3 times 4 plus h plus 5. And then we just got to do some simple algebra. We get h squared plus 5h plus 9. Okay. And now if we want to find our linear approximation, we're going to put 4 plus h into our tangent line. And we would get 9 plus 5h. All right, we want our error to be at most 0.1, so less than or equal to 0.1. All right, so remember, actual minus estimate, right? So actual minus estimate is our error. So the actual answer is h squared plus 5h plus 9 minus the estimate, which is 9 plus 5h. And if we simplify that, we end up with just h squared. The absolute value of h squared, but h squared would always be positive. So absolute value of h squared, which is of course just h squared. All right, we want the error to be less than or equal to 0.1. Okay? So if we take the square root of that, again, you can use your calculator for that. We want the absolute value of h to be less than or equal to 0.316288, or 0.316. Again, I put the absolute value bars back in there because remember, taking the square root is plus or minus. So we want h to be between negative 0.0316 and positive 0.316. Okay, that'll do it for our lesson on linear approximations. Really, all we're doing here is taking tangent lines and putting in x values that are close to the x value where the tangent line was drawn. Okay? In our next video, we're going to take a look at L'Hopital's rule, and that will end Unit 4 for us. Thanks again for tuning in today, everyone, and we'll see you next time.